Okay, today we're going to talk about modular numbers and modular arithmetic. What modular numbers are is it's a set of numbers that we say only those numbers exist and we can't even go beyond that. The most basic example of modular arithmetic is looking at a clock. On a 12-hour clock, there are 12 numbers and there's nothing else to do. So we just keep on cycling back around through that same set of numbers. We don't even denote how many times we've gone around. We just care about where we're ending. Okay? So thinking about a clock, and I'm facing the right way to be able to see a clock, because if you need to turn around and look at a clock, sometimes that helps me, like actually looking at a clock when I think about a modular arithmetic problem. If I take a 9 and I add it to a 12, so if it's 9 o'clock, what time is it 12 hours later? 9 o'clock again. Okay, so 9 plus 12 is 9.
Oh, here. So 6 plus 5 would be 1.
So 6 plus 5. If it's 6 o'clock and I go 5 hours later, it's
Oh, it'd be
11.
I don't know what I think I was saying 7.
8 plus 8. So if it's 8 o'clock, 8 hours later would be 4 o'clock.
Wait, if you divide by a certain number, does it just get your answer? If you like 8 plus 8, I don't know if this is for skill, but like if you do 8 plus 8 and it's 16 like normally, and you divide by 4 on any number, will that get you the same time?
You can't divide by 4 or 3. What we're doing is basically just taking the remainder divided by 12. So we could do 8 plus 8 is 16 divided by 12 is 1 with a remainder of 4. 4 is the answer. It's the remainder that's the answer. We don't care about how many times it went in, we just care about how much is left over. So 5 times 8, we don't really think about like multiplying hours, but I guess if you, I don't know, wanted 8 chunks of 5 hours, how many hours have passed? 40 hours, but what time is it is really what we're concerned about. So again, this is we're thinking about a remainder. So I actually get 40. I can divide that by 12. The closest multiple of 12 is 36. And so there's 4 left over. So all we care about is the remainder here. So 5 times 8 is 40. 12 goes into 40 3 times to make 36. But there's 4 left over then. 40 minus 36 is 4. So our answer in a modular question is the remainder. So 12 times 9 is, okay, thanks, 108. Then I could divide that by 12. Well, that's just getting us back to 9, right? And there was no remainder. So when there's no remainder, you just take that number back again. Six times 4 is 24.
It's 2. It's 2.
So we divide that out. And
It's 2. It's 2.
it goes in twice,
Take the number back.
Oh, I don't know.
but it goes back to where we started. You know what? I feel like that's wrong.
Wouldn't it be 2 since the other one was 9? No.
Okay. And draw out a clock.
Because if there's no remainder, wouldn't
So-
it just
We've got 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we're going to assume we're starting at 12. And we're going to do either 6 chunks of 4 hours or 4 chunks of 6 hours. It doesn't really matter which way. So if I go 6 hours 4 times, where did I land?
be 12.
12. So on that last one, if we assume again a 12 o'clock start time and go around and do 9 chunks of 12 hours, 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, it's 6.
Isn't that?
Yeah,
It's only
wouldn't it
6
be all
hours.
the way around? It's all the way around.
Oh boy.
Which
So we're
is-
back
ends
at
up
12.
But it would still be 12.
Yeah.
Yeah.
So if there's nothing left over, then it's 12. Because 12 is.
Because 12 is start time.
So it's like 0.
Yes.
So like 12 times 9 is 12, not 9.
Yes.
Yeah.
12 times 0 is 12.
Okay. I'm working this
12 times 9 is 12. You're doing it wrong. No.
Subtractions, I really need to look at a clock. So if it's 2 o'clock, 10 hours ago was
4.
4 o'clock.
I didn't. I said I go.
If it's 12, 7 hours ago was
5.
5. If it's 5, 9 hours ago was 11, 4 hours ago was 7. We call a mathematical system a group if it meets some certain criteria. So we say that it's closed. It's closed means you can't get any answer outside of itself. So if we're looking at the 12-hour clock, the only possible answers to questions are 1 to 12. We can't get any other answers, so this is closed because there's no other numbers that are going to come into our system. An identity means that if we're talking about addition, that there's something that we can add to it that will give us back itself. Or that if we're multiplying, there's something we can multiply by it that will give us back itself. Associative means that we can regroup numbers, moving around parentheses, and it won't change our answer. And inverse means that we have a way to get back to the identity value. So, if we think about addition, it's closed. We're not getting any answer other than 1 to 12. There's no way to get anything other than 1 to 12 off of a clock. If we think about identity, is there a number that I could always add to something to get me back to where I am? So what could I add to get back to where I am on the clock? 12. 12 hours later, it's going to be the same time as it is right now. So it has an identity. The identity is 12. It is associative. Proving it is a little bit harder than just kind of, if I take 1 o'clock and I add 4 hours and then add 3 hours, that's the same thing as regrouping that problem and doing the additions in a different order. Proving it is very difficult. You can do lots of examples that show it doesn't matter what order you do it in, but we're just going to go ahead and believe that it is associative here. And then an inverse would be, for every number in the system, is there a way to get an answer of 12 by adding something to it? So will it always work that I could do something plus something and get a 12 for every number in there? So 1 plus something, can I turn a 1 into a 12? I can add 11. Can I turn a 2 into a 12? I can add a 10. So will there always be a way to get 12 as an answer? 12, because that's what the identity was. Okay. So if we think about multiplication, it's still closed. We're still not getting any numbers that aren't on the clock. Is there something I can multiply by that will always give me the same answer back? 1. Right? We can always multiply something by 1. Multiplying by 1 doesn't change what a number is. Once again, it is associative, proving it's a little bit difficult, but we can move those parentheses around. Inverse. So here we have to ask, is there always a way to multiply something and get a 1 out of it? So 1 times 1, that works. Is there something I can multiply a 2 by and have it be 1? So 2 times 1 would be 2, 2 times 3 would be 6, 2 times 3, I just said would be 6. Did I say 2 times 2 would be 6? It might. This is where I'm sad that I'm recording myself because now I can go back and hear how dumb I was. So 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12. 2 times 7, that's 14, but that's really 2, right? 2 times 8 is 16, which would be 4. 2 times 9 would be 18, which is 6. 2 times 10 would be 20, which is not 1. 2 times 11 would be 22, which is also not 1. 2 times 12 would be 24, which is also not 1. So there was nothing I could do to make that turn into a 1. So there is not an inverse for every number. So here we have a fail. So that means that the 12-hour clock is not a group under multiplication. Okay, because I could not multiply a 2 by something and turn it into a 1. Okay? You're not going to have any homework problems on this idea of group today. In our next lesson, we're going to look at the idea of group further, and we'll talk about that more then.
How are you recording yourself without the recording thing?
The computer has a stronger mic than the old computer.
Oh.
All right. So scroll down and get the rest of the problems here. Okay, so find the congruent value in the given modulo. Modulo is a fancy word for modular arithmetic. So what we're doing here is turning a 19 into a 5. So remember it says the remainder, that's the answer. So we're going to say 19 divides by 5. Well, the closest multiple of 5 is what? 15, with a remainder of
1. Sorry, not 1. 4.
4.
4.
25 divided by 3. We don't care how many times it goes in. It goes in 8 times, but what we care about is what is the remainder after we take those away.
7. No. 7.
So I said the closest one was 8. 8 times 3 is
Oh,
24.
24, with a remainder of
1.
72 divided by 8, with a remainder of 0, because it actually goes in. So when we're talking about a modulo system, 0 is okay unless we're specifically talking about a clock. Clocks don't have zeros on them, but 12 is kind of like 0 on a clock.
The next ones, we have to make them into those funny numbers and then multiply them?
We don't have to.
Totally wrong.
No, we can just do the arithmetic and then give the answer
Just put it
in a certain modulo. So we can do the arithmetic to start. So 7 plus 3 is 10. And now turn that into mod 10. Our remainder is
nothing.
nothing. Another way of thinking about it is thinking like a clock with these numbers on it. So I said 0 is okay. So I'll tell my clock of 0 to 5 for mod 5. So if it's 3 o'clock and I go back 7 hours, then it's 1, 2, 3, 4, 5, 6, 7.
Wait.
Oops,
what
it
is
shouldn't have a 5.
Can I just carry you around a little clock?
Shouldn't have a 5. 5 and 0 are the same thing in a mod 5. So
Or you can draw it.
go back. 1, 2, I gave it to me. 1, 2, 3, 4, 5,
Oh, so
6,
you
7.
can't have that number
so
if
on.
you mean mod, like mod 10, you only have 9 numbers.
Yeah, you can either have it as a 0 or, so like we call it clock mod 12.
That's really
12 could be 12 or 0, but we can't have 12 and 0.
Right.
Okay, so mod 5, you could either call it a 5 or you could call it a 0, but they can't both be there. So then mod 9 You can have, my
Oh,
clock
so it
with
wouldn't
a
be 2,
zero.
it'd be 1.
Right. So here we can do just our arithmetic to start. And divide by 9. And our remainder is 4. Closest multiple of 9 is 36.
Wait, can you explain you got 1 in the one before? So you started
Yep.
at 3 and
When I do subtractions, you get -4 as an answer. So then sometimes it's hard to think about dividing -4 by a 5 because we don't want any negative answers.
Right.
So in these ones, when we have all positives, then we can just think about dividing and finding the remainder. But in negative, I like to think about moving around the clock backwards. So I start at 3 and I go backwards 7 hours. So I'm going to count down from 3. So I go to 2, to 1, to 0, around 7 times. So I go
Oh.
1, 2, 3, 4, 5, 6, 7 spaces backwards, getting at the 1. Another way to think about it is if you just do the subtraction, you get -4. Right? If I start at 5 and I go backwards 4 spots, I'm at 1. All right. So this is applied math. Things should be applicable. So a common application of modular numbers is check digits. A lot of times when you see a long string of numbers, there is one number in there that validates it, that lets somebody know that this is a true good number. So one example is driver's license numbers. There's a check digit in there so that people can't just make up a driver's license number and start using that. Then somebody who knows the setup would be able to tell that it's fake. Okay? Or credit card numbers or something like that should have check digits in them as well. UPC codes, so on everything that you buy, it has that UPC code, that long string of numbers. There's a number in there that confirms that this is a valid sequence of numbers, that somebody didn't just make up a product number. If you get a shipping label from like UPS, sometimes they'll have like what looks like a UPC code or something on it, but that's the same thing. It has some number in there that lets people know that it is in fact valid. So every type of number has its own kind of method for doing this, but driver's license number, what they do is they divide the number by a certain number that's known only to the state, and then one of the digits in there is a check digit, and they look at that remainder and make sure that it's right. But those digits are kept secret. So state of Michigan, somebody in the Michigan government knows what this check digit is. And they can take your driver's license number, divide it by whatever this number is that only they know, and find the remainder, and that number should be in your driver's license somewhere. But they keep it very mysterious because they don't want people to be able to make fake IDs. UPC codes on packages they're not as secretive about. So this example down here would be like a UPC code that would be on a product that you would buy. So what you do is you multiply the first digit by 3, the second digit by 1, then 3, then 1, and 3, then 1, on up until this very last number you don't multiply. Okay? You add all that up together, and that last digit should be whatever would make our answer count up to the next 10. So we can check this and confirm that this actually is a good UPC number. So we start with the very first digit, we multiply by 3. Then 1, 3, 1, 3, 1, 3, 1, 3, 1, 3. But we don't multiply that very last one. Okay, so then I would go on my calculator. Okay, if I'm multiplying by 0, that doesn't really matter. So then 1 times 1 is 1. 6 times 3 is 18. 0, 0, 0. And I've got an 18, a 6, a 15, a 9. And I would add those all up. Okay, so when I add them all up, I get 67. So then our check digit should be whatever it takes to make this thing go up to the next 10. So if I would add 3 to this, it would be at 70. So our check digit should be a 3.
Wait, is that for like packages?
Yes. So like when you go to the grocery store, but I don't know that it works for every
What if
product
it's wrong?
code. There might be a couple of different UPC ways that it would work, but this is one that a textbook shared, and I think I checked it in a couple places and it worked, but it's not necessarily
Why would
critical.
you check it?
Oh.
Like, what's the point of checking a UPC?
Make sure people aren't inventing product labels, or it can, I mean, when a grocery store gets new inventory in, like a new product, they would have to enter that code into the computer, so the computer knowing that this really is a true product.
Yeah.
Alright. Alright, so that is lesson 5. So, the homework is, on the back of that page of homework problems. There's 15 of them, but they are not due tomorrow. They'll be due Thursday, Thursday, because we're meeting on Thursday, and you can work on it tomorrow after your quiz.